students, and welcome to the lecture on metallic cable transmission media and optical fiber transmission media. After the lecture, we will be able to learn the following objectives. Understand the metallic cable transmission media. Explain transverse electromagnetic waves. Define metallic transmission line losses. Understand the optical fiber transmission media. Explain the propagation of light through an optical fiber cable. Discuss the losses in optical fiber cables. Let's start with a brief introduction to metallic cable transmission media and optical fiber transmission media. Transmission media are actually located below the physical layer and are directly controlled by the physical layer. One could say that transmission media belong to layer 0. A transmission medium can be broadly defined as anything that can carry information from a source to a destination. In data communications, the definition of the information and the transmission medium is more specific. The transmission medium is usually free space, metallic cable, or fiber optic cable. The information is usually a signal that is the result of a conversion of data from another form. The computers and other telecommunication devices use signals to represent data. These signals are transmitted from one device to another in the form of electromagnetic energy, which is propagated through transmission media. In telecommunications, transmission media can be divided into two broad categories: guided and unguided. Guided media include twisted pair cable, coaxial cable, and fiber optic cable. Unguided medium is free space. Let's now take a look at the metallic cable transmission media. The transmission medium is the physical path between transmitter and receiver in a data transmission system. It is included in the physical layer of the OSI protocol hierarchy. The transmission medium is usually free space, metallic cable, or fiber optic cable. Transmission media can be generally categorized as either unguided or guided. Guided transmission media uses a cabling system or some sort of conductor that guides the data signals along a specific path. The data signals are bound by the cabling system. Guided media is also known as bound media. Unguided transmission media consists of a means for the data signals to travel, but nothing to guide them along a specific path. The data signals are not bound to a cabling media, and as such are often called unbound media. Unguided transmission media are wireless systems. Let's now take a look at metallic transmission lines. A transmission line is a metallic conductor system used to transfer electrical energy from one point to another using electrical current flow. It can be used to propagate DC or low-frequency AC, and is also very high frequencies such as microwave and radio frequency signals. There are several types of transmission lines whose losses are small. The open wire line consisting of two parallel wires. The twisted pair line of two insulated wires twisted together. The concentric cable or coaxial line, where a central wire is mounted along the axis of a metal tube. Let's now have a look at transverse electromagnetic waves. The two basic kinds of waves are longitudinal and transverse. With longitudinal waves, the displacement is in the direction of propagation. A surface wave or sound wave can be examples of longitudinal waves. With transverse waves, the direction or displacement is perpendicular to the direction of propagation. Electromagnetic waves that travel along a transmission line from the source to the load are called incident waves, and those that travel from the load back towards the source are called reflected waves. Transmission line classifications. Balanced transmission line. In two-wire balanced lines, both conductors carry current. One conductor carries the signal and the other conductor in the return path. This type of transmission is called differential or balanced signal transmission. Unbalanced transmission line. With an unbalanced transmission line, one wire is at ground potential, whereas the other wire is at signal potential. This type of transmission line is called single-ended or unbalanced signal transmission. Unbalanced transmission lines have the advantage of requiring only one wire for each signal, and only one ground line is required no matter how many signals are grouped into one conductor. Metallic transmission line types. All data communication systems and computer networks are interconnected to some degree with cables, which form the most important part of the transmission medium, transporting signals between computers. Parallel conductor transmission lines. Parallel wire transmission lines are comprised of two or more metallic conductors, separated by a non-conductive insulating material called a dielectric. The most common parallel conductor transmission lines are open wire, twin lead, and twisted pair, including unshielded twisted pair, or UTP, and shielded twisted pair, or STP. Open wire transmission lines. These are two-wire parallel conductors, closely spaced and separated by air. Non-conductive spacers are placed at periodic intervals, not only for support, but also to keep the distance between the conductors constant. TEM wave propagates in the air between the conductors, which acts as dielectric. Twisted pair transmission lines. A twisted pair, or TP, transmission line is formed by twisting two insulated conductors around each other. Usually, a number of pairs of these wires are put together into a cable. The cable may contain more than 100 pairs of wires for long-distance communications. Twisted pair wires are the most common media in a telephone network. Unshielded twisted pair. A UTP cable consists of two copper wires where each wire is separately encapsulated in PVC, or polyvinyl chloride insulation. The minimum number of twists for UTP cable is 2 per foot. UTPs are cheaper, more flexible, and easier to install. They provide enough support for telephone systems. Shielded twisted pair, or STP cable. STP cable is a parallel two-wire transmission line consisting of two copper conductors separated by a solid dielectric material. The wires and dielectric are enclosed in a conductive metal sleeve called a foil. If the sleeve is woven into a mesh, it's called braid. Coaxial or concentric transmission lines. The basic coaxial cable consists of a center conductor surrounded by a dielectric material, insulation, then a concentric uniform distance from the center, shielding, and finally a rubber environmental protection outer jacket. Coaxial cables are capable of operating at higher bit rates than their parallel wire counterparts. Very secure than twisted pair cable, they can be used over long distances. They are immune to external radiation and radiate little themselves. Metallic transmission line equivalent circuit. The characteristics of a transmission line are determined by its electrical properties, like wire conductivity, insulator dielectric constant, and its physical properties, like wire diameter and conductor spacing. These properties, in turn, determine the primary electric constraints: series resistance, R, series inductance, L, shunt capacitance, C, and shunt conductance, G. Resistance and inductance occur along the line, whereas capacitance and conductance occur between the conductors. Wave propagation on metallic transmission lines. The EM waves travel at the speed of light through vacuum and nearly the same through air, but they travel considerably slowly in metallic transmission lines, where the conductor is generally copper and the dielectric materials vary with cable type. Let's now take a look at the metallic transmission line losses. Conductor losses. As electrical current flows through a metallic transmission line, there is an inherent and unavoidable power loss because of the finite resistance present in the line. This loss is termed as conductor loss or conductor heating loss. Radiation losses. Radiation and induction losses are similar in that both are caused by the field surrounding the conductors. Radiation losses are reduced by property shielding the cable. Therefore, STP and coaxial cables have less radiation than UTP, twin lead, and open wire. Coupling losses. Coupling losses occurs whenever a connection is made to or from a transmission line, or when two divisions of transmission line are connected together. Discontinuities are the locations where dissimilar materials meet, and they tend to heat up, radiate energy, and dissipate power. Let's now learn about optical fiber transmission media. An optical communication system is one that uses light as the carrier of information. They use glass or plastic fiber cables to contain the light waves and guide them in a similar manner to the way EM waves are guided through a metallic transmission media. Advantages of optical fiber cables. Immunity to static interference. As optical fiber cables are non-conductors, they are immune to electromagnetic interference, or EMI, caused by lighting, electric motors, relays, fluorescent lights, and other electrical noise sources. Lower transmission loss. Fiber optic cables offer less signal attenuation over long distances. Typically, it's less than 1 dB per kilometer. Security. Optical fibers are more secure as they are almost impossible to tap into because they do not radiate signals. No ground loops exist between optical fibers, hence they are more secure. Durability and reliability. Optical cables last longer and are more reliable than metallic facilities because fiber cables have a higher tolerance to changes in environmental conditions and are immune to corrosive materials. Electromagnetic spectrum. The electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. The electromagnetic spectrum of an object is the characteristic distribution of electromagnetic radiation emitted or absorbed by that particular object. The frequency spectrum extends from the subsonic frequencies, a few hertz, to cosmic rays, 1023 hertz. The light frequency spectrum can be divided into 3 general bands as infrared, visible, and ultraviolet.
From fiber optics for sale. In this video, I will explain what is fiber optics, so let's get started. From its name, we know that fiber optics is composed of fiber and optics. Here, fiber is a very thin plastic or glass strand. Optics means light. So fiber optics basically means light that travels in a strand of plastic or glass fiber. This picture shows a bunch of fiber enclosed in a single black color protective jacket. So how is light guided and travels inside the fiber? This video shows a beam of light that travels inside a water stream by total internal reflection. Optical fibers work the same way, so let's take a look. The previous video gives us a basic idea of how light would travel inside a fiber. Now let's see what a glass fiber is composed of. A glass fiber has a cylindrical structure and is composed of 3 layers. At the center is a core. Core has higher refractive index. Outside of core is the cladding layer. Cladding layer has lower refractive index than the core. The third layer is a plastic buffer coating. This buffer coating layer doesn't affect the fiber's optical performance. It is there for mechanical protection only. The right picture shows how light is coupled into the fiber's core and bounced back and forth in the core and travels along the fiber. The core and cladding layers are all based on fused silica, which is a type of glass. But this fused silica is extremely clear, with almost no impurities. This transparency is extremely important, so that the light can travel for a very long distance, such as hundreds of kilometers with minimum loss. This makes trans-Pacific and transcontinent fiber optic communications possible. Here comes the question, why doesn't the light leak out of the fiber? That is why we have to explain the phenomenon of total internal reflection. The left picture shows Snell's law, which guides how light travels at the interface of the core and cladding. The core has a higher refract index, n equals 1.5. The cladding has a lower refract index, n equals 1.4. When light incidents at the interface between the core and the cladding at different angles, some power is reflected back, and some power enters into the cladding, which is refracted. But when we increase the incident angle to greater than a critical angle theta c, no more light enters into the cladding. All light is reflected back into the core. This phenomenon is called total internal reflection. The important point here is the critical angle theta c. If light enters the fiber less than theta c, it will quickly leak out of the fiber and won't travel long. When the light enters the core at an angle greater than theta c, it will be bounced back and forth at the interface of core and cladding and travels very long distance along the fiber with very low loss. This picture visually shows the total internal reflection process. The manufacturing of glass fiber goes through two steps. In the first step, a preform is made. This preform has exactly the same proportion of core and cladding material as final fiber product, but in a much bigger size. It looks like a thick glass rod, as shown in the bottom picture. Then the preform is hung at the top of fiber drawing tower. The tower is a couple stories tall, as shown in the right picture. The preform is heated by a furnace which softens the glass. The softened glass drips and is pulled downward by gravity. A diameter monitor carefully monitors the fiber's diameter, which usually is 125 micrometers. Then the coater deposits a layer of plastic buffer coating for mechanical protection, which usually is 250 micrometers in diameter. And finally, the fiber is winded onto a spool for storage and transportation. A basic fiber optic communication system must have at least three components. The light source, which usually is a laser. The laser is turned on and off quickly by a driving circuit. In this modulation process, the original electronic signal is translated into light signal. The second part is the fiber. The fiber's purpose is to transmit the light through a very long distance, such as from New York to Paris. And the third part is a photodetector. The photodetector detects the light and generates electronic current. In this process, it translates the light signal back into electronic signal. Of course, real-world systems are much more complicated, but this gives you a rough idea of how it works. This illustration shows the laser modulation process, which turns the laser on and off by an electronic signal. The laser generates stable, continuous light. The most common light colors or wavelengths are 850 nanometer, 1310 nanometer, 1550 nanometer, and more. The light itself is an electromagnetic wave and is called the carrier wave, as shown here. The top is the electronic signal, which has much lower frequency than the carrier wave itself. When this signal is used to turn the laser on and off, the bottom illustration shows the generated pulse, which is a low-frequency signal envelope modulated on top of the high-frequency carrier wave. The most common signal speeds include 100 megabit per second, 1 gigabit per second, 2.5 gigabit per second, 10 gigabit per second, 40 gig per second, and 100 gigabit per second. 100 gigabit per second is currently a state-of-the-art technology, and many fiber optic companies are working hard to commercialize it.
Let's now learn about the optical fiber communication system block diagram. The three primary building blocks are transmitter, receiver, and the optical fiber cable. The transmitter is comprised of a voltage to current converter, a light source, and source to fiber interface. The fiber guide is the transmission medium, which is either an ultra-pure glass or a plastic cable. The receiver includes a fiber to interface, a photodetector, and a current to voltage converter. Optical fiber construction. There are two basic types of fiber optic cable. The difference is whether the fiber is free to move inside a tube with a diameter much larger than the fiber, or is inside a relatively tight-fitting jacket. They are referred to as loose tube and tight buffer cables. Let's now have a look at the velocity of propagation. Refraction. It is the bending of light when the light passes from one medium to another. The angle between the light ray and the normal as it leaves a medium is called the angle of incidence. The angle between the light ray and the normal as it enters a medium is called the angle of refraction. Refractive index. Refractive index is simply the ratio of the velocity of propagation of light ray in free space to the velocity of propagation of a light ray in a given material, given by n equals c over v, where n is refractive index and c is speed of light, meters per second, and v is speed of light in a given material, meters per second. Critical angle. The angle of incidence is called the critical angle, which is defined as the minimum angle of incidence at which a light ray may strike the interface of two media and result in an angle of refraction of 90 degrees or greater. Let's now look at the propagation of light through an optical fiber cable. Light can be propagated using either refraction or reflection, and the way light propagates depends on the mode of propagation and the index profile of the fiber. Modes of propagation. Mode simply means path. If there is only one path for light rays to take down a cable, it's called single mode. And if there's more than one path, it's called multi-mode. In single mode, the light travels directly down the center of the cable, whereas for multi-mode, light rays propagate down the cable in a zigzagging fashion. Index profile. Index profile of an optical fiber is a graphical representation of the magnitude of the refractive index across the fiber. A step index fiber has a central core with a uniform refractive index. A graded index fiber has no cladding and the refractive index of the core is non-uniform. It is highest at the center of the core and decreases gradually with distance towards the outer edge. Optical fiber modes and classifications. Three practical types of optical fiber configurations are single mode step index, multi-mode step index, and multi-mode graded index. Single mode step index optical fiber. The fiber has a central core that is sufficiently small that there is essentially only one path for light ray to go through the cable. In most cases, the outside cladding is air, making this fiber have a wide external acceptance angle, making it relatively easy to couple to a light source. Multi-mode step index optical fiber. These are similar to single-mode step index fibers, except that the center core is much larger with the multi-mode configuration. This type has a large light-to-fiber aperture, and therefore allows more external light to enter the cable. Light rays travel down the cable in a zigzag fashion, continuously refracting off the interface boundary. Light rays travel in many paths as it propagates down the fiber. Multi-mode graded index optical fiber. These fibers are characterized by a central core with a non-uniform refractive index. Cable's density is maximum at center and decreases gradually towards the edge. Light ray is propagated through refraction. As the light propagates across the core towards the center, it intersects a less dense to more dense medium. This cable is mostly used for long-distance communication. Now we will discuss losses in optical fiber cables. Power loss in optical fiber cables is often called attenuation and results in reduction of power of light wave as it travels down the cable. Transmission losses in optical fibers result in reduction of light power, thus reducing the system bandwidth, information transmission rate, efficiency, and overall system capacity. The predominant losses are absorption losses. It is analogous to power dissipation in copper cables, as impurities in the light fiber absorb the light and convert it to heat. Radiation losses. These are caused predominantly by small bends, wand kinks in the fiber. The two types of bends are microbends, and constant radius bends. Microbending occurs as a result of differences in the thermal contraction rates between core and cladding material and results in a material bend along the axis of the fiber and represents a discontinuity where Rayleigh scattering occurs. Coupling losses. These losses are caused by imperfect physical connections. These occur at three types of junctions: light source to fiber connections, fiber to fiber connections, and fiber to photodetector connections. Let's now have a look at light sources. Light sources are used in fiber optic communication to generate light pulses at wavelengths efficiently propagated by this optical fiber. They also should produce sufficient power to allow the light to propagate through the fiber without causing distortion in the cable or receiver. Two types of practical light sources used to generate light for optical fiber communication systems are light-emitting diodes, or LEDs, and injection laser diodes, or ILDs. Light-emitting diodes. LEDs emit light by spontaneous emission. Light is emitted as a result of the recombination of electrons and holes. LEDs can provide light output when forward biased. The LED has a low output power, slower switching speed, and greater spectral width, hence more dispersion. Injection laser diode. ILDs are similar to LEDs, and they act similarly below a certain threshold current. Above the threshold current, an ILD oscillates and lasing occurs. The radiant output power of ILD is more directive than LED. After lasing occurs, the optical power increases dramatically, with small increases in drive current. Light detectors. Two devices are commonly used to detect light energy in optical fiber communications receivers: PIN, P-type intrinsic N-type diodes, and APD, avalanche photodiodes. PIN diodes are the most common device used and operate just the opposite of an LED. APDs are more sensitive than PIN diodes and require less additional amplification. Lasers. Laser stands for light amplification stimulated by the emission of radiation. It deals with the concentration of light into a very small, powerful beam. Four types of lasers are gas lasers, liquid lasers, solid lasers, and semiconductor lasers. Now in the end, let us summarize what we have learned in this lecture. A transmission line is a metallic conductor system used to transfer electrical energy from one point to another using electrical current flow. A physical facility is one that occupies space and has weight opposed to wireless media, such as the Earth's atmosphere or a vacuum, and includes metallic cables and optical cables. Propagation of electrical power along a transmission line occurs in the form of transverse electromagnetic waves. Waves travel at different speeds depending on the type of wave and the characteristics of the propagation medium. In two wire balanced lines, both conductors carry current. One conductor carries the signal and the other conductor in the return path. This type of transmission is called differential or balanced signal transmission.